The universe is broadcasting secrets we are only beginning to hear. For decades, our most powerful radio telescopes have been picking up strange, fleeting signals from the depths of space. These are not the steady hum of stars or the predictable pulses of dead suns. They are sudden, brilliant screams of radio energy that vanish in milliseconds, or cryptic patterns that repeat on a cosmic clock. Today, we are diving into the evidence for 40 of the most unexplained radio signals ever detected from outside our galaxy. By the end, you will understand the leading theories behind these cosmic enigmas and what they reveal about the most violent events in the cosmos. We will explore a signal so shocking it was literally circled with the word "wow," and another that burst to life on a precise 16-day schedule. What does it mean to listen for whispers in an infinite cosmic static? The story of these 40 signals begins with a single, lonely blip on a screen. In 2001, a young astronomer named Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia. He was looking for something else entirely, new pulsars perhaps, when he stumbled upon an anomaly. Buried in observations from 1998 was a spike of radio energy so intense it overwhelmed the telescope's instruments. It lasted just 5 milliseconds, a cosmic flashbulb popping in the dark. The most shocking part was its origin. By measuring how the burst's different frequencies were stretched and delayed, a property called dispersion, Lorimer calculated it had traveled for billions of light years. This came from far, far outside our Milky Way galaxy. It was the first documented fast radio burst, now known as the Lorimer Burst. The scientific community met the discovery with deep skepticism. A signal that powerful from that far away, lasting only thousandths of a second, defied all known physics. Many argued it had to be a glitch, local interference from a passing satellite, or even a microwave oven in the observatory kitchen. For years, the Lorimer Burst stood alone, an unexplained oddity that many dismissed as a cosmic mirage. It would take more than a decade and the discovery of many more such bursts for researchers to finally accept they were looking at a genuine and terrifyingly energetic new class of astrophysical event. That one 5-millisecond blip, almost deleted and forgotten, quietly opened a door to a universe far more violent and mysterious than we had imagined. That first lonely blip was not the beginning of our listening. Decades before Duncan Lorimer's discovery, another signal had already ignited the imagination of the world. It came from a humble instrument in the Ohio countryside called the Big Ear Radio Telescope. On the night of August 15, 1977, this telescope was part of the Search for Extraterrestrial Intelligence project, patiently scanning the sky for any pattern that seemed crafted, not chaotic. The data was printed out on long sheets of paper, columns of letters and numbers representing the strength of incoming radio waves. Most days, the printouts showed nothing but the gentle hiss of cosmic static. But on that night, something extraordinary happened. For 72 seconds, the telescope's fixed gaze swept over a patch of space near the constellation Sagittarius, and its receiver recorded a signal so powerful and so strange that it defied all natural explanation. The next day, astronomer Jerry Amon was reviewing the data, his eyes scanning the lines of alphanumeric code. His routine check turned to stunned disbelief. In one column, he saw the sequence 6EQUJ5. This code represented a signal that jumped in intensity to 30 times the background noise, held that peak, and then faded away as the telescope moved on. Amon, a man of science not given to exaggeration, took his red pen, circled the entire sequence, and wrote a single, emphatic word in the margin: "Wow." That red ink immortalized the wow signal. Its properties are what made astronomers' hearts race. First, it was a narrowband signal, meaning it was concentrated on one very specific radio frequency, just like our own radio and television broadcast. Natural cosmic objects like pulsars or gas clouds typically emit a broad smear of radio noise across many frequencies. This precision was a hallmark of technology. Second, it lasted exactly 72 seconds, which was the precise amount of time the Big Ear's field of view took to pass over a fixed point in the sky. This meant the signal's intensity rose and fell in a perfect curve, a telltale signature of a distant, stationary source. It came from interstellar space far beyond our solar system. In that one brief moment, it seemed as if the universe had cleared its throat and spoken directly to us. And then it fell silent forever. In the decades since, that same patch of sky has been observed thousands of times by far more sensitive instruments. Not a single beep, not a whisper, not a trace of that powerful signal has ever been heard again. Its one-time appearance makes it impossible to verify or study further, transforming it from a scientific datum into a permanent cosmic mystery. The WOW signal remains the purest, most tantalizing maybe in the history of the search for other minds in the cosmos. A 72-second enigma that continues to echo in our collective curiosity. The WOW signal was a cosmic whisper that never spoke again, but the universe had not finished surprising us. In 2016, a discovery shattered a fundamental assumption about these powerful radio bursts. For years, the prevailing theory was that fast radio bursts were one-time cataclysms, the final death screams of unimaginably violent events. If a star is ripped apart by a black hole or a neutron star collapses, it happens once. You would only hear that signal a single time, but then astronomers found FRB 121102. This particular burst, first detected in 2012, did something extraordinary. It came back. After its initial detection, the Arecibo telescope in Puerto Rico caught it flaring up again and again, a cosmic beacon flickering on and off with no discernible pattern. This was the first repeater. Its repeating nature changed everything. Because it kept coming back, scientists could point the world's most powerful radio telescope arrays at its coordinates with patience, waiting for it to flash again. That patience paid off. They were able to triangulate its location with stunning precision, pinning it not just to a galaxy, but to a very specific kind of galaxy. FRB 121102 lives in a tiny, faint dwarf galaxy over 3 billion light-years away. This small, messy galaxy is a stellar nursery, churning out new stars at a frantic rate. The environment around the repeater itself provided another clue. Alongside the sporadic, brilliant millisecond bursts, astronomers found a faint, constant radio hum emanating from the same spot. This persistent radio source suggests something powerful and ongoing is sitting there, like a raging engine idling between explosive revs. The leading theories for what that engine could be now center on two extreme objects. The first is a magnetar, an intensely magnetic type of neutron star. Think of a city-sized object with a magnetic field 1 trillion times stronger than Earth's, capable of starquakes that crack its crust and unleash titanic energy. The second possibility is an active galactic nucleus, the supermassive black hole at the galaxy's core, devouring matter and spewing out jets of radiation. The repeater proved these signals were not just one-off fireworks. They could be lighthouses powered by something that persists, something we could eventually understand. It turned a mystery of destruction into a puzzle of ongoing cosmic power. The discovery of a repeater was only the first step into deeper strangeness. If a signal could come back, could it also keep a schedule? In 2019, a new telescope in Canada called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, made a discovery that seemed to defy belief. It found a repeating fast radio burst with a cosmic heartbeat, catalogued as FRB 180916. This signal bursts to life on a precise, predictable rhythm. For approximately 4 days, it fires off frequent, brilliant flashes of radio energy. Then, as if a switch is flipped, it falls completely silent for about 12 days. This cycle of activity and quiet repeats every 16.35 days with the regularity of a clock. This was not a chaotic explosion or a random sputter. This was a pattern, a structure written into the fabric of a distant galaxy billions of light years away. The existence of such a clear periodicity is a colossal clue. It tells us that whatever engine is powering these bursts is not acting alone. It is part of a system, its violence choreographed by an external cosmic clock. The leading theory to explain this 16-day cadence involves orbital motion. Imagine a binary system, a pair of stars locked in a gravitational dance. One member could be a super-dense, highly magnetic neutron star or a magnetar. As this object orbits its companion, perhaps a massive star or a black hole, there are phases in its orbit. For a few days each cycle, it passes through a region where conditions are just right for it to unleash its beams of radio energy directly toward Earth. This could be a cloud of material stripped from its companion star that fuels the bursts, or a point where the star's own magnetic field is most unstable. Then, for the rest of its long orbit, it is either pointed away from us or in a calmer environment, resulting in the 12 days of radio silence. Another compelling idea is precession. A spinning magnetar does not always spin perfectly upright. Like a wobbly top, its axis of rotation can slowly circle around, a process called precession. The beams of radiation it emits shoot out from its magnetic poles. If one of those wobbly poles periodically sweeps across our line of sight every 16 days, we would see a window of activity followed by a long period where the beam points off into empty space. This predictable pattern, whether from an orbit or a wobble, transforms the source from a mere mystery into a celestial machine we can begin to dissect. It suggests a level of organization in the chaos, a violent process tamed by the simple, elegant rules of orbital mechanics. The universe is not just screaming at us, it is sending messages in Morse code with a timing so precise we can set our watches by it. That predictable 16-day rhythm showed us these bursts could be part of a system, but it left a burning question unanswered. What kind of object could survive such repeated titanic explosions? A discovery in 2019 provided a stunningly clear picture, a cosmic crime scene with the suspect still at large. This is FRB 190520, a repeater that behaves like nothing we have ever seen. It was found by China's 500-meter fast telescope, the largest single-dish radio telescope on Earth, in a relatively nearby dwarf galaxy just 3 billion light-years away. In the vast scale of the cosmos that is practically our backyard, its relative proximity made it an instant celebrity for astronomers, a close-up laboratory to study the engine behind these bursts. What they found was a signal with a split personality. First, it is hyperactive, bursting far more frequently and energetically than other known repeaters. Second, and most importantly, it lives with a constant companion. From the exact same point in space, astronomers detected a faint, unending radio glow. This is called a compact, persistent radio source. It is not the burst itself, but a steady hum that continues whether the brilliant millisecond flashes are happening or not. Think of it like a raging forest fire. The fast radio bursts are the sudden, explosive crackles of a tree igniting. But the persistent radio source is the smoldering embers and thick smoke that hang in the air long after each crackle dies down, a permanent testament to the ongoing conflagration. This afterglow is the crucial clue. Its properties match what theorists predicted for a very specific environment, a nebula powered by a newborn magnetar. Here is how that story might unfold. When a massive star dies in a supernova, its core can collapse into a neutron star. If that neutron star is born spinning incredibly fast and with an unimaginably powerful magnetic field, it becomes a magnetar. In its violent youth, this infant magnetar would be surrounded by the expanding debris of its own birth, a shell of supernova material. the magnetar's fierce winds and radiation would slam into this shell, energizing it and causing it to glow brightly across the radio spectrum. That glowing shell is the persistent radio source we detect. Meanwhile, the young, unstable magnetar itself is prone to colossal starquakes and magnetic eruptions on its surface. Each of these cataclysmic events could blast out a beam of radio waves, which pierces through the surrounding nebula and reaches us as a fast radio burst. FRB 190520, with its brilliant bursts and its permanent radio haze, fits this portrait perfectly. It appears to be a cosmic toddler, a magnetar only decades or centuries old, still screaming within the crib of its own supernova remnant. Its discovery provides the strongest evidence yet that at least some of these mysterious signals are the birth cries of the universe's most magnetic monsters. Because it is so relatively close and so brilliantly active, it offers our best chance to watch this dramatic stellar adolescence unfold in real time. But magnetars are not the only possible source for a cosmic signal. What if some of these 40 whispers are not natural at all? This brings us to a signal that emerged not from a professional observatory, but from the collective processing power of millions of personal computers around the world. In 2004, the distributed computing project SETI at home announced a tantalizing candidate. For years, this project had allowed volunteers to donate their computers' idle time to analyze mountains of radio telescope data, searching for the subtle signature of an artificial transmission. The software was designed to flag anything unusual, and it found something it labeled SETI 02+14A. On the surface, its properties were eerily promising. The signal appeared at a frequency of about 1,420 MHz, a quiet region of the radio spectrum often called the waterhole, a band scientists speculate might be used for interstellar communication. More intriguingly, the signal's frequency drifted. It wasn't a perfect, steady tone. It shifted slightly over time in a way that precisely matched what you would expect if the transmitter were placed on a rotating planet. As the planet turns, the motion would cause a Doppler shift, minutely stretching and compressing the radio waves, just like the pitch of a siren changes as an ambulance passes by. This drift suggested a transmitter anchored to a world spinning in space, a technological beacon, not a natural cosmic object. The signal seemed to originate from a point in the sky between the constellations Pisces and Aries, a region with no obvious stars or planets nearby. For a moment, it felt like the dream of SETI at home had been realized, a potential needle found in the cosmic haystack by the global public. Yet, almost immediately, profound skepticism set in. The signal was extremely weak, hovering right at the threshold of what the equipment could detect. It was only picked up 3 separate times and never again from that same location despite repeated searches. Critics argued it was far more likely to be random radio interference, perhaps a glitch from a passing satellite or even terrestrial sources reflecting off space debris, masquerading as an extraterrestrial broadcast. The very nature of the distributed project made verification a nightmare, with data processed in tiny chunks on thousands of different computers. Pinpointing a consistent, localized source of interference was nearly impossible. SETI 02+14 stands as a perfect symbol of the immense challenge in this search. It embodies the heartbreaking pattern of a promising signal that fades into ambiguity, a ghost in the machine of citizen science. It reminds us that for every one real cosmic event, there are millions of mimics, and the greatest skill in listening to the universe is not just hearing a whisper, but proving it did not come from our own backyard. The possibility of a signal from our own tools is a haunting reminder of how difficult this search truly is. Yet in April 2020, the universe delivered a gift of absolute clarity, a signal that cut through decades of speculation. It came not from the distant depths of intergalactic space, but from our own cosmic neighborhood. On April 28th, a known magnetar in our Milky Way galaxy, called SGR 1935 plus 2154, suddenly woke up. This city-sized remnant of a dead star, located about 30,000 light-years away in the constellation Vulpecula, had been sporadically spitting out X-ray bursts for years. But on that day, it did something unprecedented. It unleashed a colossal eruption so powerful it was detected in two completely different forms of light. Space-based telescopes like NASA's Swift and Fermi caught an intense millisecond flash of high-energy X-rays and gamma rays. At the exact same millisecond, two radio telescope systems on Earth lit up. The CHIME array in Canada and a smaller, purpose-built network of antennas called STARE-2, spread across California and Utah, both recorded a brilliant, short burst of radio waves. This was FRB 2004-28, the first fast radio burst ever detected originating within our own galaxy. The correlation was perfect and undeniable. The same object at the same instant screamed in X-rays and shouted in radio waves. This was the smoking gun. For the first time, astronomers could point to a specific type of celestial object and say with certainty, this can produce a fast radio burst. The magnetar's extreme magnetic field, a quadrillion times stronger than Earth's, is the key. Theorists believe the burst was triggered by a massive starquake, a sudden rearrangement of the magnetar's rigid crust under unimaginable magnetic stress. This quake likely launched a blast wave of charged particles into the surrounding space, which then interacted with the magnetar's own intense magnetic field. That interaction is what generated the simultaneous flash of X-rays we saw and the coherent beam of radio waves that traveled to Earth. The radio burst itself, while monumental for science, was thousands of times weaker than those coming from other galaxies. This fact alone was a revelation. It meant that the truly colossal fast radio bursts we detect from billions of light-years away must be produced by events far more energetic than even this spectacular galactic outburst. FRB 2004-28 did not solve the entire mystery, but it provided a foundational piece of the puzzle. It proved that magnetars are indeed one of the universe's engines for these signals, turning a leading hypothesis into an observed fact. Suddenly, the most distant, powerful bursts no longer seemed like theoretical phantoms. They were simply the same process turned up to an almost inconceivable volume echoing across the cosmic deep. The discovery of a galactic fast radio burst gave us a known culprit, but the ultimate dream of this search is to find a signal that is not natural at all. This brings us to one of the most tantalizing and ultimately sobering chapters in the modern hunt for extraterrestrial intelligence. In late 2020, headlines around the world blared a stunning announcement. Astronomers with the Breakthrough Listen project using the Parkes radio telescope in Australia had detected a candidate signal unlike any other. It was named BLC-1, Breakthrough Listen Candidate 1. What made this signal so electrifying was not its power, but its address. It appeared to come from the direction of Proxima Centauri, the closest star to our own Sun, a mere 4.2 light-years away. Even more compelling, we know this star hosts a planetary system, including a rocky world called Proxima Centauri b, orbiting within the star's habitable zone where liquid water could exist. For a moment, it seemed the universe had delivered the perfect story, a signal from next door from a star known to have a potentially Earth-like world. The signal itself checked several intriguing boxes. It was a narrowband transmission, concentrated on a single radio frequency of 982 MHz, a band typically quiet from natural cosmic processes. It also exhibited a frequency drift, a slight shift in its tone over time, consistent with a transmitter placed on the surface of a rotating planet. The data showed the signal persisted for several hours during multiple observations, and it was only present when the telescope was pointed at Proxima Centauri. When the telescope moved away, the signal vanished. This directional specificity was perhaps the most compelling evidence of all. The excitement within the small team was palpable, a mix of professional caution and the undeniable thrill of a potentially historic discovery. They followed protocol, dubbing it a candidate and not a detection, and embarked on a year-long forensic analysis. This is where BLC-1 transforms from a potential first contact into a masterclass in scientific skepticism. The team left no stone unturned. They examined every possible source of human-made radio frequency interference, from satellites and aircraft to ground-based electronics. They used other telescopes to observe the same star system, searching for a repeat of the signal that never came. The breakthrough and the disappointment came from a deeper dive into the signal's properties. While it drifted in frequency, the drift did not match the precise motion you would expect from a planet orbiting Proxima Centauri. More critically, when researchers analyzed the signal using a different set of receivers at Parkes, they found faint traces of it even when the telescope was not pointed at the star. The final conclusion, published over a year after the initial detection, was definitive. BLC-1 was human-made radio frequency interference, almost certainly from a device on the surface of the Earth. Its appearance aligned with Proxima Centauri due to a coincidence of timing and the complex way the telescope sweeps the sky. This case is not a failure but a necessary fire drill. It demonstrates the extreme, painstaking levels of verification required in a field where the stakes are the highest imaginable. A single mistake, a moment of rushed excitement, could echo through history. BLC-1 is a monument to that caution, a ghost signal from our own technology that reminded everyone listening that the hardest signal to find will be the one that is genuinely not our own. The search for a signal source is often a hunt for the right environment, a specific cosmic neighborhood where such violence makes sense. Yet one of the 40 signals refuses to follow the rules. It is known as FRB 2020-0120E, a repeating burst that lives in the last place anyone expected to find one. This cosmic rebel was traced to the outskirts of a beautiful spiral galaxy called M81, a neighbor just 12 million light-years away. But its precise location was the shock. It did not reside in a messy star-forming region or near the galaxy's turbulent core. Instead, it was pinpointed to a globular cluster, a dense, ancient ball of stars orbiting M81 like a distant, fossilized satellite. This discovery sent a tremor through astrophysics. Globular clusters are cosmic retirement homes. They contain some of the oldest stars in the universe, quiet red dwarfs and aging giants that formed over 10 billion years ago. They are not nurseries for young, massive stars. According to everything we thought we knew, they should be the last place to find a magnetar, the presumed toddler of the stellar world. A magnetar is the remnant of a short-lived, colossal star that explodes after only a few million years. Such a star would have lived, died, and vanished billions of years before the ancient stars in this cluster even finished forming. So what is creating these powerful radio bursts in a place where the engine should not exist? The presence of this repeater forces us to consider alternative, even stranger origins. One leading idea is that of a cosmic vampire. Imagine an old, slow-spinning neutron star, the quiet corpse of a star that died long ago. In the dense core of a globular cluster, stars pass close to one another frequently. This dormant neutron star could have found a binary companion, perhaps a normal star or a white dwarf. Over eons, it could be siphoning material from its partner. This infalling gas, spiraling onto the neutron star's surface, could spin it up to incredible speeds and potentially rejuvenate its magnetic field, effectively creating a magnetar-like object billions of years after its birth. It is a stellar resurrection. Another, more exotic possibility points to a different kind of dense object entirely, a highly magnetized white dwarf. White dwarfs are the Earth-sized cores of dead sun-like stars, and some rare types possess enormously strong magnetic fields. A catastrophic event on or around such a white dwarf, like a giant flare or a collision with another object in the crowded cluster, could theoretically unleash a burst of radio energy matching what we see. FRB 2020-0120E is a rule breaker. It tells us that the universe may have more than one way to build a radio beacon. The violent processes we seek might not only be the birth cries of young monsters, but also the sudden, late-life awakenings of ancient ones stirring in the deep quiet of a cosmic graveyard. The ancient stellar graveyard of a globular cluster shows us these signals can emerge from unexpected places. But what if the source was not a star at all, but something on a scale that defies comprehension? This brings us to a different kind of whisper, one written not in radio waves but in heat. In 2015, astronomers studying data from NASA, a wise space telescope which scans the sky in infrared light, noticed something peculiar about a distant galaxy cluster called SEO 3325. One galaxy within it was radiating a colossal, anomalous amount of infrared light. It was not the bright, focused glow of a central black hole, but a diffuse, galaxy-wide warmth. To understand why this was so startling, we need a framework for thinking about advanced intelligence. In the 1960s, astronomer Nikolai Kardashev proposed a scale to classify civilizations by their energy use. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization captures the total energy output of its home star, perhaps by building a theoretical structure like a Dyson sphere. A Type 3 civilization, a concept almost beyond our imagination, would command the energy output of its entire galaxy. The infrared glow from that distant galaxy was, for a brief and thrilling moment, considered a potential signature of such a Type 3 civilization. The reasoning was based on a simple law of physics. Energy cannot be created or destroyed, only transformed. If a civilization were using the light of every star in its galaxy, that vast amount of energy would eventually be converted into waste heat, radiating away as infrared light. The anomalous galaxy in cluster SEO 3325 seemed to be doing exactly that, shining with an unexplained infrared signature that some researchers argued could be the exhaust fumes of a galaxy-spanning society. It was a hypothesis that captured the public imagination, a candidate for the greatest technological footprint imaginable. The scientific process, however, demands that extraordinary claims be met with extraordinary evidence. Follow-up studies with more powerful telescopes began to dissect the mystery. Researchers looked deeper, analyzing the specific wavelengths of infrared light and searching for other telltale signs of natural processes. They found them. The most likely explanation was not cosmic engineering, but cosmic dust. This galaxy appears to be undergoing an immense, dust-obscured burst of star formation. Vast clouds of silicate and carbon-rich dust, generated by previous generations of stars, envelop the galaxy. This dust absorbs the visible and ultraviolet light from the brilliant newborn stars and re-radiates it as the diffuse infrared glow that WISE detected. It is a natural, if extreme, astrophysical phenomenon, not a technological one. The story of this candidate is a vital lesson in cosmic humility. It demonstrates the powerful allure of the idea that we are not alone, and the even greater power of rigorous investigation to separate the wondrous possibilities of nature from the still unfound dreams of intelligence. The universe is full of natural miracles that can mimic our grandest fantasies, and listening to its whispers requires us to hear what is actually there, not just what we hope to find. Among the ancient quiet of globular clusters, another signal blazes with youthful, relentless fury. FRB 2019-0520b is not a faint whisper from a cosmic retirement home. It is a constant, screaming siren from the edge of the universe. Discovered by China's colossal fast telescope, this repeater is one of the most active and energetic sources we have ever found. It does not burst once and vanish for months. It erupts frequently, unpredictably, and with staggering power, offering astronomers a rare and precious gift, a non-stop broadcast from a cosmic engine. Its first clue is written in its dispersion measure, the telltale smear of its radio waves across different frequencies. This measure is incredibly high, meaning the signal has passed through an immense amount of material during its journey. That long, cluttered path places its home galaxy billions of light years away in the deep cosmic past. Yet despite that staggering distance, its bursts are so brilliant and so common that we can study them in exquisite detail. This hyperactivity transforms it from a mystery into a living laboratory. Because it flashes so often, scientists can point the world's most sensitive instruments at its coordinates and simply wait, knowing another burst is likely just hours or days away. This allows them to capture each flash with incredible precision, analyzing a property called polarization. Think of light or radio waves as vibrations. Normally, these vibrations can be oriented in any direction, like a rope being shaken in a chaotic, random wiggle. Polarized light, however, vibrates in a single, clean plane, like that same rope being shaken perfectly up and down. The radio bursts from FRB 2019-05-20b are highly polarized. This is a crucial clue because it tells us the waves have traveled through a powerful, structured magnetic field. The magnetic field acts like a cosmic filter, forcing the chaotic vibrations to align. But the story gets even more fascinating. Scientists have watched as the angle of this polarization, the specific direction of the vibration, subtly rotates from burst to burst. This rotation, called Faraday rotation, is like a cosmic fingerprint. It reveals that the magnetic environment around the source is not static. It is dynamic and complex, perhaps churned by violent winds from a newborn magnetar or twisted by the turbulent plasma of a surrounding nebula. Each brilliant flash from this distant dwarf galaxy is not just a shout of energy. It is an encoded message about the invisible magnetic forces that shape its violent home. By listening to its frequent cries, we are not just hearing an explosion. We are mapping the magnetic architecture of a cosmic catastrophe in real time. That constant siren from the distant universe shows how much we can learn when a signal repeats. But what happens when we only hear a whisper once from a place that feels hauntingly familiar? In August 2015, a different kind of signal briefly seized the world's attention. The Ratan 600 radio telescope in Russia, a giant ring of antenna panels nestled in the Caucasus Mountains, detected a strong, narrowband radio spike. Its origin was not some distant, anonymous galaxy. It appeared to come from the direction of a star called HD 164595, a sun-like star just 95 light-years away in the constellation Hercules. This star is a near twin to our own sun, slightly older and a little less massive, and astronomers knew it had at least one Neptune-sized planet orbiting it. The potential implications were immediate and electrifying. A signal from a sun-like star in our cosmic backyard with a known planetary system. For a few days, the story ignited a media frenzy, with headlines speculating about a possible transmission from an advanced civilization next door. The signal's reported properties added to the intrigue. It was a strong, narrowband burst at a frequency of 11 GHz, a band used for satellite communications and radar here on Earth. The researchers who found it, led by Italian astronomer Claudio Maccone, were appropriately cautious, labeling it a candidate and calling for urgent international follow-up observations to confirm its extraterrestrial origin. But that confirmation never came. By the time the news reached other major radio observatories like the Allen Telescope Array in California, weeks had passed. They pointed their dishes at HD 164595 and heard nothing but the usual cosmic silence. Without that immediate, simultaneous verification, the signal faded from a potential discovery into a lingering question mark. In the months that followed, the most plausible explanations emerged from much closer to home. Analysis suggested the signal's characteristics closely matched those of a military or surveillance satellite transmission, possibly from a Russian or Chinese satellite that happened to pass through the telescope's field of view. Other possibilities included terrestrial interference reflecting off space debris, or even a glitch in the telescope's own complex data processing system. The case of the HD 164595 signal is a masterclass in the critical importance of timing in this search. A single detection, no matter how promising, is essentially a scientific dead end without instant, independent verification. It becomes a ghost, impossible to prove or disprove, forever hovering in the realm of tantalizing what-ifs. This event underscored a hard truth for astronomers. The universe does not wait for our schedules or our peer review process. A real signal from the stars would require us to be listening with a global network, ready to triangulate and verify at a moment's notice, because some cosmic whispers are spoken only once. While some repeaters hide in ancient star clusters, another chose a far more familiar neighborhood. FRB 2021-124 announced itself with a storm of over 1,800 separate bursts, recorded over just 54 hours by China's Fast Telescope. This incredible activity provided a flood of data, but the real revelation came when astronomers pinpointed its home. It resides not in a distant dwarf galaxy, but in a grand spiral galaxy much like our own Milky Way. More precisely, it was localized to a spiral arm, a stellar nursery rich with the glowing gas and young, massive stars that are the raw materials for cosmic violence. This location is a powerful clue. Spiral arms are where short-lived, colossal stars are born, live fast, and die young in supernova explosions. Placing the repeater here strongly supports the leading theory that its engine is a young magnetar, perhaps only decades or centuries old, born from one of these recent cataclysmic deaths. It is a signal emerging from a stellar maternity ward, a newborn's cry echoing from the bustling, star-forming suburbs of a cosmic city. The sheer volume of bursts allowed scientists to perform a kind of high-speed magnetic biopsy on its environment. As they analyzed the polarization of each flash, they witnessed something bizarre and unprecedented. The Faraday rotation, that telltale twist in the radio waves caused by magnetic fields, began to swing wildly. It changed dramatically, not over months or years, but from one burst to the next, sometimes within mere hours. This was like watching a lighthouse beam flashing through a storm. The clear, steady signal was being scrambled by something turbulent and chaotic lying directly between the source and us. The leading explanation paints a dynamic and violent portrait. The magnetar, the likely source of the bursts, is not sitting in empty space. It is likely orbiting another object, perhaps a massive, hot companion star. As it moves along its orbit, it is plowing through the fierce stellar wind and the tangled magnetic field boiling off its partner. Each time it fires a radio burst, that beam must punch through a different, shifting patch of this magnetized plasma. The sudden changes in Faraday rotation are the fingerprints of that turbulent screen. One moment, the beam passes through a relatively calm region. The next, it slices through a maelstrom of charged particles, twisting the signal in a new way. This data suggests we are not just looking at a solitary explosive object, but at a dramatic binary dance, a cosmic partnership where one member's furious energy is filtered and shaped by the violent atmosphere of the other. The turbulent binary dance of a spiral arm shows us how a signal's environment can twist its message. But what if the environment itself promised a world like our own? In 2008 and 2009, a series of unconfirmed whispers seemed to point directly at a star system that had already captured our imagination. Gliese 581 is a small, dim red dwarf star just over 20 light-years away. What makes it special are its planets. At the time, astronomers had identified several worlds orbiting within its habitable zone, the temperate region where liquid water could exist on a rocky surface. One, Gliese 581G, was even heralded as a prime candidate for a potentially Earth-like world. It was against this backdrop of profound possibility that an Australian team using the Hobart 26-meter radio telescope reported something extraordinary. They claimed to have detected several strong, narrowband radio signals, each lasting only minutes, emanating from the precise direction of the Gliese 581 system. The signals were not random noise. They appeared to be concentrated at specific frequencies, a hallmark of potential technological origin. For a moment, it felt like a cosmic door had creaked open. Here was a nearby star with promising planets, and now it seemed to be broadcasting. The news sparked a wave of excitement and immediate scrutiny within the SETI community. The protocol in such cases is clear and demanding. Independent verification is everything. Major radio observatories around the world, including the giant Allen telescope array dedicated to this search, swiftly trained their dishes on Gliese 581. They listened intently across a wide range of frequencies, employing sophisticated algorithms to sift for any sign of the reported transmissions. They heard nothing. No repeat of the brief, strong bursts, no persistent carrier wave, only the eternal, natural hiss of the cosmos. The signals detected by the Hobart team were never heard again by any other instrument. This outcome highlights a fundamental and frustrating challenge known as the SETI paradox. The most likely signal we might detect from another civilization would not be a continuous, easily found beacon. It would be transient, perhaps a powerful radar pulse for mapping asteroids, or a brief, directed communication burst. These signals are, by their nature, fleeting. They flash into existence and are gone, often before any other telescope on Earth can swing into position to confirm the detection. A single observatory might catch a whisper, but by the time the alert goes out to the global network, the moment has passed, leaving behind only a tantalizing, unverifiable data point. The Gliese 581 candidates join a long list of such ghosts, signals that flicker at the edge of certainty before vanishing into the static of doubt. They underscore a painful truth in the search for other minds. The universe is vast, quiet, and does not repeat itself for our convenience. To find a real signal, we do not just need to be listening. We need the entire world to be listening at once, ready to capture a whisper that may never come again. While fleeting whispers dominate this mystery, one signal arrived with a thunderclap and left a ghostly echo. FRB 2011-24 was not just a brilliant flash, it was a cosmic event with a lingering shadow. Detected in November 2020 by the ASCAP array in Australia, this burst was astonishingly luminous, one of the brightest ever recorded. But its true distinction lay in what happened after the initial millisecond blast faded. Astronomers using the ultra-sensitive Very Large Array in New Mexico kept watching the point of origin, and there for 3 weeks they saw a faint, diffuse glow of radio waves. It was an afterglow, a slowly fading ember from the site of a cosmic explosion. This persistent radio source was not the compact hum of a magnetars nebula like we saw with FRB 1905-20. This was something far more extended and ephemeral, a cloud of energized particles drifting through the void. The leading theory to explain this tale is a shockwave plowing through space. Imagine the initial fast radio burst as a titanic lightning bolt, a sudden release of energy so intense it blasts a shell of material outward at nearly the speed of light. This shell, a shockwave of charged particles, then smashes into the thin gas that drifts in the space between stars within its host galaxy. That collision is violent. It energizes the gas, causing it to glow in radio wavelengths for weeks as it slowly expands and cools. This faint, fading afterglow is the glowing wreckage of that impact. For scientists, this tale is not just a curiosity, it is a powerful new tool. By studying how quickly the afterglow fades and its specific radio signature, they can indirectly measure the density and even the composition of the otherwise invisible material it is traveling through. It is like seeing the wake of a speedboat on a dark lake. The shape and spread of the waves tell you about the properties of the water you cannot see. This particular burst's long-lived echo suggests it exploded into a relatively dense environment, perhaps a region rich with gas and dust near a stellar nursery. Each burst that leaves such a trace becomes a probe, using its own destructive power to illuminate the dark, tenuous highways between the stars, mapping the unseen architecture of its faraway galactic home. That fading afterglow gave us a glimpse of a shockwave's path, but some signals arrive with no echo at all, only a story that lingers in the margins of science. In the early 1990s, a rumor began to circulate among astronomers and SETI enthusiasts. Researchers from the University of Western Sydney, it was said, had detected something remarkable. Their radio telescope had allegedly picked up a strong, narrowband signal, a clear and steady tone that seemed to originate from the Tau Bootes star system. This was not a random point in the sky. Tau Bootes is a sun-like star only about 51 light-years away, and in 1996, a massive gas giant planet was discovered orbiting it extremely closely, a scorching hot Jupiter. The idea of a signal from a known planetary system, even before that planet was officially found, sent a ripple of excitement through the community. The reported characteristics were classic SETI wish fulfillment. A narrowband signal is the fingerprint of technology, not nature. It suggested a carrier wave, a deliberate broadcast, not the chaotic radio emissions of stellar flares or interstellar gas. For a moment, it seemed like a potential breakthrough hiding in Australian data. Yet, that is where the story stops and the mystery begins. The detection was never formally published in any peer-reviewed scientific journal. No detailed data sets were released for other teams to analyze. No official announcement ever came from the University of Western Sydney. The signal remained and still remains an anecdote, a piece of oral history in the SETI world. Why would such a potentially monumental discovery vanish into silence? The reasons are likely pragmatic and sobering. In radio astronomy, the first and most critical step is ruling out terrestrial interference. A signal that looks perfect can be a passing satellite, a television transmitter, a piece of electronic equipment in the observatory, or even a distant aircraft's radar reflecting off a metal building. Without an immediate, independent verification from a second telescope hundreds of miles away, any single detection is suspect. The researchers involved, facing the immense burden of proof and likely unable to redetect the signal themselves, may have chosen caution over announcement. To publish a claim of an extraterrestrial signal and be wrong is a professional risk few are willing to take. The Tau Bootes mystery signal thus became a permanent footnote, a ghost in the early days of the planet-hunting era. It stands for all the unverified whispers, the tantalizing blips that appear on a screen one night and are never seen again, the data points too fragile to bear the weight of the hope they inspire. The ghost stories of unverified signals remind us how fragile these cosmic whispers can be, but a recent discovery arrived with such clarity it forced us to rewrite the rulebook. In September 2022, the CHIME telescope captured a repeating burst designated FRB 2209-12A. At first glance, it was another brilliant repeater from a distant dwarf galaxy, but a deeper look at its radio fingerprint revealed something bizarre, a detail that physicists are still struggling to explain. This signal is known as the riser. To understand why, picture the sound of a musical chord. Most fast radio bursts are like a chord where the low notes are overwhelmingly loud and the high notes are faint, almost inaudible. This is because of the nature of the violent events that create them and the plasma they travel through, which tends to scatter and absorb higher frequencies. But parts of FRB 2209-12 did the exact opposite. Certain components within its millisecond flash actually got brighter at higher radio frequencies. The notes rose in volume as they climbed the scale. This rising spectrum is a direct challenge to the standard models of how these bursts are born. The prevailing theories all involve what is called synchrotron emission, where electrons spiraling at nearly the speed of light around magnetic fields release radiation. In almost every known astrophysical environment, this process naturally produces more power at lower frequencies. The riser defies that expectation. It suggests the environment around the source, or the emission mechanism itself, is far more exotic than we have accounted for. One possibility is that we are seeing the burst pass through an incredibly unusual screen of magnetized plasma on its way to us, a cosmic lens that selectively amplifies the higher pitches. Another, more radical idea is that the engine itself operates in a regime of physics we rarely see, perhaps involving quantum processes or coherent emission from dense, magnetized objects in ways our current equations cannot easily describe. This single, strange signal tells us that the universe has more than one way to scream. It complicates the beautiful, simple story we were starting to tell about magnetars and shock waves, forcing us to acknowledge that the plasma physics of the cosmos holds depths of mystery we are only beginning to probe. The riser's defiance of physics shows how much we still have to learn, but for every signal that challenges our models, there are dozens that vanish before we can even name them. This brings us to a different kind of mystery, one defined not by a single brilliant flash, but by a haunting pattern of absence. For years, the Allen Telescope Array in California, a field of 42 white radio dishes built specifically for the search for extraterrestrial intelligence, has been conducting wide, systematic surveys of the sky. Its computers are programmed with sophisticated filters designed to catch the hallmarks of an artificial broadcast. They look for narrowband signals, sharp spikes of energy concentrated on one specific radio frequency, the kind of clean tone a transmitter makes, not the messy roar of a star. And they find them quite often. In fact, the array's logs are filled with candidates, signals that pass every initial test for something that could be technological. The story should then be one of triumphant discovery, but it is not. Because every single time, without exception, when astronomers go back to look, when they point the dishes at that same coordinate and listen again with even greater care, the signal is gone. It never repeats. These are the Allen Telescope Array anomalies, a graveyard of perfect ghosts. Each one is a whisper that seemed to say hello, only to dissolve into the static when we tried to reply. So what are they? The leading explanations are frustratingly mundane, yet each reveals a layer of complexity in our modern sky. The first and most likely culprit is our own technology, specifically undisclosed satellite transmissions. The space around Earth is increasingly crowded with satellites, many of them military or commercial with unpublished broadcast frequencies. A secret satellite could pass through the telescope's field of view, send a brief, narrowband burst for a moment, and then move on, never crossing that same patch of sky in the same way again during follow-up observations. Another possibility involves the atmosphere itself. Radio waves from a distant television tower or a passing aircraft's radar can bounce off patches of charged gas in the upper atmosphere, a phenomenon called atmospheric reflection. This can create a brief, distorted echo that appears to come from a fixed point in deep space, mimicking an extraterrestrial signal before the atmospheric conditions change and the phantom vanishes. But there remains a sliver of possibility for something truly cosmic. Could some of these ghosts be a rare, natural astrophysical maser we do not yet understand? A maser is like a laser, but for microwave or radio frequencies. In space, natural masers occur when molecules like water or silicon monoxide in clouds around stars are energized, amplifying specific radio frequencies into intense narrowband beams. We know of stellar and galactic masers, but what if there are transient, ultra-brief versions, flaring up in unexpected places and then fading forever? Such a phenomenon would be a new astrophysical beast, one that perfectly impersonates the signature we are desperately hoping to find. these anomalies represent the quiet, grinding reality of the search. They are the constant background of almost discoveries, the reminders that the universe and our own planet is filled with echoes and mirages. To find a real signal, we must first learn to recognize every single way the cosmos and our own technology can lie to us. A ghost from our own galactic backyard might be hiding among the 40 signals. FRB 2018-1030 stands out not for its power or repetition, but for what it lacks. Its dispersion measure, the telltale smear that reveals how much material its radio waves have traveled through, is remarkably low. This number is so small it presents astronomers with a fascinating puzzle. The burst could be a relatively nearby extragalactic event, originating from a galaxy just beyond the borders of our Milky Way. Or, more provocatively, it could be a source within the vast, diffuse halo of our own galaxy, a spherical cloud of ancient stars and hot gas that extends far beyond the familiar spiral disk. A low dispersion measure is like a clean window. Most fast radio bursts come to us from billions of light years away, their signals scrambled and filtered by eons of travel through the magnetized plasma that floats between galaxies. That journey imprints a complex signature on the burst, making it hard to see the original signal clearly. But FRB 2018-1030 appears to have taken a much shorter, cleaner path. With less cosmic static in the way, its radio fingerprint is simpler, less corrupted. This gives scientists a rare opportunity to study the intrinsic properties of the burst engine itself, to hear its voice before it gets distorted by the long journey. The challenge lies in pinpointing its true distance. Is it a faint whisper from a neighboring galaxy, or a shout from a previously unknown object lurking in the dim outskirts of our own cosmic home? Distinguishing between a very nearby extragalactic source and a distant source within our galaxy's halo is incredibly difficult with a single, non-repeating burst. It is the astronomical equivalent of hearing a voice in a fog. Is the speaker just a few feet away, talking softly, or is it someone far off, shouting with all their might? Without a precise location tied to a specific galaxy, the burst remains in a tantalizing limbo. Its very clarity becomes the source of its mystery, a clean signal that refuses to reveal where it cleaned itself. That clean, nearby signal remains a puzzle of distance, but one star's mystery was built on a different kind of silence. KIC 8462852, known as Boyajian star, captured the world's imagination not for what it broadcast but for what it blocked. The Kepler Space Telescope revealed its light would dip in bizarre, irregular patterns, sometimes by a staggering 22%. No planet, no matter how large, could cause such a dramatic and jagged eclipse. For a thrilling moment, the most exotic explanation on the table was a Dyson swarm, a vast constellation of energy-collecting structures built by an advanced civilization, partially obscuring the star. If a civilization were capable of such cosmic engineering, might they also be broadcasting? This question triggered one of the most intense radio listening campaigns in SETI history. Teams used the Green Bank Telescope in West Virginia and the Allen Telescope Array in California to scan Boyajian star across a wide range of frequencies. They listened for both narrowband signals, the hallmark of a deliberate beacon, and broadband leakage, the sort of radio noise a technologically active society might emit by accident, like our own television and radar transmissions. The result, after hundreds of hours of observation, was a profound and telling quiet. With one fleeting exception, the radio dial on this strange star was dead. That single exception came from the Russian Ratan 600 telescope, which reported a tentative, weak narrowband signal, but like so many others, it was never heard again. No other observatory could confirm it, and follow-up searches found nothing. This universal radio silence became a powerful argument against the alien megastructure idea. The reasoning is compelling. A civilization capable of building a structure that obscures a fifth of a star's light would be unimaginably advanced. Their energy usage would be colossal, and harnessing that energy would likely involve technologies that produce significant radio frequency emissions, either as a byproduct or for communication. The fact that we hear absolutely nothing, not even the faint radio whisper of a planetary civilization like our own, suggests that whatever is blocking Boyajian star's light is not technological. It is likely a natural, if extraordinary, phenomenon. The current favored explanations involve swarms of comets on chaotic orbits, or vast clouds of interstellar dust and debris passing in front of the star. The radio telescopes did not find aliens, but they performed a crucial service. By hearing nothing, they helped steer the investigation back toward the natural cosmos, reminding us that sometimes the most important signal is the one we never receive. The profound silence from Boyajian star taught us the power of negative evidence, but some signals announce themselves with a roar from the very edge of everything. FRB 220610 is not just another burst, it is a candidate for the cosmic long-distance champion. When it flashed into existence in June 2022, its most striking feature was not its brightness but its fingerprint. Astronomers measured its dispersion measure, that telltale smear of its radio frequencies, and the number was staggering. This single value, the DM, is the key to unlocking a burst journey. As a radio signal travels across the universe, it passes through a sea of invisible, ionized particles, free electrons floating in the space between stars and galaxies. Each electron it encounters causes a tiny delay, and higher frequency radio waves are delayed less than lower ones. The result is that the signal arrives stretched out, with its lower notes arriving a fraction of a second after its higher ones. The greater the total smear, the more electrons the signal has plowed through, and therefore the longer its journey has been. It is a cosmic odometer measured in electrons per cubic centimeter. To estimate a true distance, astronomers perform a careful cosmic accounting. They first subtract the contribution from the ionized material within our own Milky Way galaxy, a known quantity mapped by other telescopes. Then, they must estimate the contribution from the burst's own host galaxy, which is trickier. What remains, the vast majority of the dispersion measure, is attributed to the diffuse fog of the intergalactic medium, the thin plasma that fills the voids between galaxies across cosmic time. The number for FRB 220610 was so enormous it sent a clear message. This signal had traveled through an almost inconceivable amount of that intergalactic fog. Initial estimates placed its origin at a distance of around 8 billion light-years. To put that in perspective, this burst began its journey to us when our Earth was only about half its current age, and the most complex life forms on the planet were single-celled organisms. It is a messenger from the universe's adolescence. Such an extreme distance pushes our models of the cosmos to their limits. The dispersion measure depends on our understanding of how much ionized material exists between galaxies across the vast span of cosmic history. A burst from this far away acts as a probe of the early universe's conditions, testing our theories about how the cosmic web of matter formed and evolved. If its distance is confirmed, it means the event that created it was almost unimaginably energetic, a cataclysm so powerful its radio scream remained audible across more than half the observable universe. This record-holding candidate is more than a distant flash. It is a benchmark proving that these cosmic explosions can illuminate not just galaxies, but the very fabric of space-time itself. The record-holding burst from 8 billion light-years away shows us the universe's raw power, but some of the most perplexing whispers came not from deep space but from a staff lunchroom. For years, the Parkes radio telescope in Australia was plagued by a series of bizarre signals it dubbed Puritans. Named after a mythical winged stag, these signals were the ultimate cosmic pranksters. They looked for all the world like genuine fast radio bursts. They were short, millisecond blips of radio energy, Most damningly, they exhibited that telltale smear across frequencies, a dispersion measure that suggested they had traveled through vast amounts of interstellar plasma. This was the signature of a deep space origin, yet there was one glaring inconsistency. These peritons only ever appeared when the telescope was pointed low on the horizon, and they seemed to come from every direction at once. A true astrophysical signal comes from one fixed point in the sky. These were coming from everywhere, as if the source was all around the observatory itself. For a long time, they sowed genuine confusion, muddying the data and making astronomers question whether some percentage of the distant bursts they were cataloging might actually be these local phantoms. The mystery persisted until a team decided to install a new, real-time radio interference monitor at the site. Then, in early 2015, they caught one in the act. The periton signals were not arriving from the cosmos. They were erupting from the observatory's kitchen, specifically from its microwave oven. The mechanism was brilliantly mundane. When someone heated their lunch and then stopped the microwave before the timer had fully counted down, they would open the door while the magnetron, the device that generates the microwaves, was still briefly active. This released a short, powerful burst of radio frequency interference. If this happened at the precise moment the massive, sensitive Parkes dish was sweeping across that sector of the sky, the telescope would capture the burst. The dispersion-like signature was a red herring created by the telescope's own complex electronics as they processed the sudden, local blast of noise. The periton mystery, once a confounding puzzle, became a legendary cautionary tale. It underscores a fundamental, humbling truth in the search for cosmic whispers. Before you can claim a discovery from the edge of the universe, you must first prove it did not come from the break room next door. While most of these cosmic screams last mere milliseconds, one signal refused to be rushed. FRB 2019-12-21, did not flash, it roared. Detected by the CHIME telescope in December 2019, this event shattered all expectations by lasting a staggering 3 whole seconds. To put that in perspective, a typical fast radio burst is a camera flash, over in a fraction of an instant. This was a sustained spotlight, blazing across the radio spectrum for thousands of times longer than any burst we had seen before. Its duration alone would have been enough to rewrite the textbooks, but the signal had another secret. Within that 3-second roar, astronomers found a clear, repeating pattern. Embedded in the data was a distinct periodic pulse, a steady beat repeating every 0.2 of a second like a cosmic metronome ticking inside the Fury. This rhythmic structure is what truly blurred the lines of our understanding. We know of objects in space that pulse with such clockwork regularity, pulsars. These are rapidly spinning neutron stars, lighthouses of the cosmos that sweep beams of radiation past Earth with every rotation, often hundreds of times per second. We also know of magnetar giant flares, catastrophic eruptions on the surface of highly magnetic neutron stars that can release more energy in a fraction of a second than our Sun will emit in 100,000 years. FRB 2019-12-21 seemed to be a bizarre hybrid, possessing the sustained power of a colossal flare, but structured with the precise rhythm of a pulsar's spin. So what kind of object could possibly produce this? One compelling theory points to a very slow, very old magnetar. Most pulsars and magnetars we observe spin incredibly fast, completing a rotation in mere seconds or even fractions of a second. But what if this object is a cosmic elder, a magnetar that has been slowing down for eons, its rotation now stretched out to a leisurely several seconds? A massive starquake or magnetic eruption on its surface could then trigger a ringing aftershock that lasts for multiple full rotations, allowing us to see its slow, steady pulse embedded within the longer explosion. Another, more exotic idea is that we are not seeing the spin of a star at all, but the orbit of something around it. Imagine a neutron star with a dense asteroid or planetary fragment in a close, rapid orbit. Each time this debris plows through the neutron star's intense magnetic field or crashes onto its surface, it could trigger a burst of radio emission. The orbital period of the debris, not the star's spin, would then create the precise rhythm we detect. This long-duration signal forces us to question our very categories. Is it an extraordinarily long, fast radio burst, or an extraordinarily bright and distant pulsar we caught during a cataclysmic event? It suggests the zoo of cosmic radio transients is more interconnected than we thought, and that the same fundamental engines, neutron stars and their immense magnetic fields, can produce a breathtaking spectrum of signals from millisecond chirps to 3-second symphonies with a beat. The 3-second symphony with a steady beat showed us how strange a single signal could be, but the search for patterns has sometimes led us to see messages where none exist. In the 1970s and 80s, a known cosmic beacon became the center of an extraordinary controversy. The Geminga pulsar, a dense stellar corpse spinning about 4 times per second in the constellation Gemini, was already a fascinating object. It was one of the closest pulsars to Earth, and it emitted powerful gamma rays but was strangely quiet in radio waves, making it a puzzle in its own right. But some researchers began to report something even stranger in the data. They claimed to see anomalous signals superimposed on Geminga's regular metronomic pulses. These were not random noise, but subtle, structured variations that some interpreted as a potential modulation, a coded signal riding on the natural lighthouse beam. The idea ignited a firestorm of speculation. If these anomalies were real, what could they mean? Pulsars were already perfect natural timekeepers, their pulses so regular they rival atomic clocks. What if an advanced civilization, recognizing this, had chosen a pulsar as a cosmic bulletin board? They could, in theory, modify its emission slightly, imprinting a message onto the most reliable signal in the galaxy. Geminga, being so relatively close, became the prime candidate for such a cosmic post office. The public imagination, fueled by the era's science fiction, eagerly embraced the notion. Here was a real object in the sky that might be both a natural wonder and an artifact of intelligence, a star turned into a transmitter. The scientific reality, however, proved far less sensational. As other teams scrutinized the data with more advanced techniques, the case for the anomalies crumbled. The strange variations were traced to instrumental artifacts, subtle quirks in the early detection equipment that could mimic a signal. Other explanations pointed to our still evolving understanding of pulsar emission physics itself. Pulsars are not simple radio bulbs. Their beams are generated in complex, magnetized regions above their surfaces, where processes like plasma turbulence and wave interactions can create intricate subpulses and drifting patterns that might look artificial to an untrained analysis. The Geminga signals were ultimately debunked, a classic case of seeing a face in the clouds. Yet, the episode left a profound legacy. It cemented in the public mind the powerful metaphor of pulsars as cosmic lighthouses, not just for navigation but for communication. It also taught a rigorous lesson to the scientific community. The line between a revolutionary discovery and a compelling illusion is often drawn by the limits of our own technology and understanding. Before we can hear a whisper from another mind, we must first learn all the ways our own instruments can whisper to us. That slow, rhythmic burst challenged our categories, but another signal was stretched thin by the very fabric of space itself. FRB 2020-0430 arrived not as a sharp crackle but as a drawn-out sigh. Its most defining feature was an extreme level of scattering, a profound smearing of its signal in time. To understand scattering, picture a beam of light entering a frosted glass window. The smooth, clear beam hits the uneven, textured surface and scatters in all directions. Some rays take a direct path, while others bounce around the microscopic imperfections, arriving at your eye a tiny fraction of a second later. The result is not a sharp image, but a soft, diffuse glow. Radio waves traveling through space can experience the same effect. Instead of glass, the obstacle is turbulent, magnetized clouds of plasma, soup-like regions of ionized gas and free electrons. As the sharp, millisecond radio pulse from a fast radio burst passes through one of these clouds, the different waves within the pulse are jostled and deflected by the chaotic, churning material. They take slightly different paths, like runners navigating an obstacle course with random barriers. By the time they exit the cloud and continue toward Earth, they are no longer in lockstep. The once clean pulse is stretched out, its leading edge arriving normally, but its tail dragged out into a long, fading echo. FRB 2020-0430 was subjected to this process on an epic scale. Its signal was so heavily scattered it was like hearing a gunshot echo down a long, winding canyon. The extreme nature of this smearing is a critical clue written in distortion. It tells us the burst did not take a clean, empty path. It punched directly through an exceptionally turbulent and dense screen of plasma. But where was this screen? Two compelling possibilities exist, each turning the burst into a cosmic probe. The first is that the signal passed through the chaotic halo of its own host galaxy. Galactic halos are vast, spherical regions of hot gas, dark matter, and leftover debris that envelop galaxies like a faint, gaseous atmosphere. This halo is not serene. It can be stirred by supernova explosions, galactic winds, and mergers with smaller galaxies, creating pockets of intense turbulence. If the burst source was positioned such that its beam had to travel through a particularly violent section of this halo before escaping into intergalactic space, that journey alone could cause the severe scattering we observed. The second possibility points to the spaces between galaxies. We often think of the intergalactic medium as a near-perfect vacuum, but it is not empty. It is a web of incredibly thin but still present ionized gas. At certain nodes in this cosmic web, where filaments of matter intersect, the density of this plasma can be significantly higher. If the burst's path to Earth happened to cross one of these dense knots, that knot could act as the scattering screen. In either case, the burst becomes more than just a message. It becomes a diagnostic tool. By measuring precisely how its signal was stretched and smeared, astronomers can indirectly map the properties of the invisible material it traveled through. They can estimate the density and turbulence of that plasma cloud billions of light years away, using the burst's distorted echo to illuminate structures we could never see directly. This heavily scattered whisper is a reminder that the universe is not just empty space between points of light. It is filled with a turbulent, magnetized medium, and sometimes the clearest signal we can get about that hidden ocean is the distorted shape of a wave that has passed through it. Scattered signals reveal the universe's hidden structure, but one of history's most famous whispers had a far more terrestrial source. During the height of the Cold War, a bizarre and persistent anomaly plagued the American embassy in Moscow. For years, starting in the early 1950s and intensifying through the 1970s, embassy staff were subjected to a mysterious bombardment. It was not a sound or a visible light, but an invisible, low-level beam of microwave radiation focused directly on the upper floors of the building. This became known as the Moscow signal. At first, the effect was simply perplexing. Diplomats and their families reported unexplained health issues, from persistent headaches and fatigue to more severe concerns. The strange energy was measurable, a constant humming presence in the air of the embassy, but its purpose was utterly opaque. In the tense atmosphere of superpower espionage, theories immediately spiraled. Was it a Soviet mind control experiment, a weapon designed to sow illness and confusion among American personnel? Or, given the era's growing fascination with flying saucers and unexplained phenomena, could it be something not of this Earth at all? The signal's mysterious nature and its origin from an unseen source made it a perfect canvas for UFO speculation. It seemed like a classic case of a technologically advanced, non-human intelligence conducting surveillance, a notion that captured the public imagination for decades. The truth, when it finally emerged from declassified intelligence, was both more mundane and more ingeniously sinister. The microwave beam was not an alien probe or a psychic weapon. It was a sophisticated espionage tool. Soviet intelligence had likely seeded the embassy's construction materials, or even its very walls, with passive listening devices called resonant cavities. These were simple pieces of metal with no power source or circuitry of their own that could be activated remotely. The constant, low-power microwave beam served as the remote control. When the microwaves hit these hidden cavities, they would cause them to vibrate minutely. Any sound in the room conversations, the clicking of a typewriter, the turning of a page, would cause the cavity to vibrate slightly differently. The beam would then reflect back to a Soviet receiver, carrying those tiny, sound-modulated vibrations. The Soviets could then decode the reflected signal, effectively listening through the walls without ever planting a single traditional bug. The Moscow signal was a brilliant, if unsettling, piece of spycraft. Its legacy as a cosmic mystery, however, endures as a powerful lesson. It demonstrates how easily the combination of geopolitical secrecy, advanced but hidden technology, and human fear can conjure a story of otherworldly visitors. When we cannot see the source of a strange energy, our minds naturally reach for the most extraordinary explanations. This incident reminds us that before we attribute a signal to intelligence beyond our world, we must first exhaust every possibility of intelligence very much within it, especially when that intelligence is engaged in a silent, invisible war. A single, sharp crack is one thing, but a cosmic echo within itself is something else entirely. FRB 2018-11-12 did not arrive as a clean pulse. Instead, its millisecond flash contained a distinct double-peaked structure, like a single gunshot followed an instant later by its own perfect reverberation. The signal rose to a peak of intensity, dipped slightly, and then rose again to a second, nearly identical peak just a few milliseconds later. This was not noise or scattering. This was a clean, structured fingerprint written into the very heartbeat of the burst, a clue to the geometry of the cataclysm that created it. So what kind of event creates a signal with two faces? The models scientists have built to explain this double peak are like different blueprints for the same catastrophic machine. One compelling idea returns us to the concept of a binary dance. Imagine two ultra-dense objects, perhaps neutron stars or magnetars, orbiting one another in a tight, furious embrace. If both objects are capable of producing their own bursts, a flare on one might be followed milliseconds later by a sympathetic eruption on its partner, triggered by a shock wave or a magnetic coupling across the tiny gap between them. We would see two distinct bursts, one from each member of the pair, separated by the light travel time across their orbital distance. Another, more subtle possibility involves cosmic lensing. Between us and the distant source of the burst, an invisible object might drift, a star, a black hole, or even a dense cloud of dark matter. As the radio flash from the burst passes by this object, its immense gravity can act like a lens bending the path of the light. Some of the radio waves take a direct route to Earth, forming the first peak. Others are bent along a slightly longer, curved path, arriving a few milliseconds later to create the second, identical peak. It would be a natural echo, a ghost created by the warped space-time around an unseen foreground object. But perhaps the most elegant explanation lies in the emission process of a single spinning object. Picture a highly magnetic neutron star, its surface racked by a colossal quake. The eruption might not be a single point-like explosion. It could involve two distinct, powerful hotspots on the star's surface, or a single hotspot that is beamed in such a complex way by the star's twisted magnetic field that its radiation reaches us in two separate waves. As the star spins, even minutely during the millisecond event, one emission region could come into view, then another, creating that double pulse in our detectors. Each of these models' binary partners, gravitational lensing, or a complex single source paints a different physical picture of a distant catastrophe. The double peaks of FRB 2018-11-12 are more than a curiosity. They are a high-resolution snapshot of an event that normally passes in a blur, offering a level of detail that lets us discriminate between whole families of theoretical models. In that split-second echo, we are not just hearing a bang, we are hearing the shape of the bang itself. The line between a cosmic mystery and a human story is often blurred by our own longing. In 1997, a story erupted that seemed to answer one of astronomy's greatest questions. It began with a photograph from a wheat field in England near the Chilbolton radio telescope. There, pressed into the crops, was a complex circular pattern. To many, it looked uncannily familiar. It bore a striking resemblance to the famous Arecibo message, the binary encoded radio signal beamed toward the star cluster M13 in 1974 by astronomers Frank Drake and Carl Sagan. The original Arecibo message was a pictorial plaque for the cosmos. Its pattern of ones and zeros, when decoded, depicted our solar system, the chemical formulas for DNA, a stick figure of a human, and the Arecibo telescope itself. The crop circle that appeared 23 years later seemed to be a reply. It mimicked the same rectangular grid format but with key, chilling alterations. The solar system diagram was changed to show 3 inner planets with the third, representing Earth, prominently highlighted. The DNA double helix was altered. The human stick figure was replaced with a larger-headed, shorter-bodied silhouette, and the depiction of the telescope at the bottom was swapped for a representation of the very crop circle formation itself, as if signed by its maker. For a moment, it felt like a cosmic closure. The wow signal, that powerful, unexplained radio spike from 1977, had never been explained. Here, it seemed, was the answer, not a radio signal, but an artifact, a physical response etched into the English countryside. The narrative was irresistible. An alien intelligence had received our message, decoded it, and sent back a corrected version, identifying our world and describing themselves. The media frenzy was immediate and global. The story tapped into a deep cultural nerve, the profound human desire for contact, for confirmation that we are not alone in the silent dark. It was a perfect myth for the modern age, blending cutting-edge science with ancient folklore of circles in the fields. The euphoria, however, was short-lived. Investigators and skeptical scientists quickly dismantled the fantasy. The evidence was overwhelmingly terrestrial. The formation appeared overnight in a secluded field, a feat impossible for a single person, but well within the capability of a dedicated team of human circle makers using simple boards and ropes. The design, while complex, contained subtle errors in its binary coding that a truly advanced species would likely not make. Most damningly, the entire concept was flawed. The original Arecibo message was beamed toward a cluster of stars 25,000 light-years away. Even if someone was there to receive it the moment it arrived, a reply would take another 25,000 years to return. A response in 1997 was a physical impossibility. The crop circle was a brilliant, elaborate hoax, a piece of land art designed to provoke and deceive. Yet its impact was real. It demonstrated how the search for extraterrestrial intelligence is not just a scientific endeavor, it is a cultural mirror. When the universe offers us silence, we are sometimes tempted to fill it with the stories we most wish to hear. The Chilbolton hoax did not advance astronomy, but it revealed something fundamental about the audience here on Earth. We are listeners in a quiet room, so eager for a voice that we can mistake the echo of our own hopes for a whisper from the stars. The magnetic echo of a burst can map a hidden universe. Among the 40 signals, one stands out for the intense fingerprint it carries. FRB 2021-0117 was not the brightest or the most repetitive burst we have found, but it holds a record of a different kind. It possesses an exceptionally high rotation measure. To understand why this matters, picture the burst's radio waves as vibrations traveling through space. Normally, these vibrations can wiggle in any direction, but if they pass through a powerful magnetic field, that field acts like a cosmic comb, forcing all the vibrations to align in a single, clean plane. This is called polarization. The rotation measure tells us something more subtle: how much that clean plane of vibration has been twisted during the journey. The stronger the magnetic field the signal passes through, and the more dense the plasma in that field, the greater the twist. FRB 2021-0117A's radio waves arrived severely twisted. This high rotation measure is a direct, quantifiable message. It tells us the burst did not travel through empty, calm space. It punched through an environment of ferocious magnetism. So where does such a powerful magnetic field exist? One terrifying possibility places the burst's origin in the most violent neighborhood imaginable, the immediate vicinity of a supermassive black hole. At the heart of many galaxies, these monsters spin, surrounded by an accretion disk of superheated gas and a corona of magnetized plasma. A burst generated near this maelstrom would have to escape through these intensely magnetized layers, acquiring an extreme rotational twist on its way out. Another compelling scenario returns to the idea of a binary system. Imagine the burst source, perhaps a magnetar, in orbit with a massive, luminous companion star. That companion would be blowing out a fierce stellar wind, a torrent of charged particles carrying the star's own magnetic field out into space. As the magnetar moves along its orbit, any burst it emits must travel through this churning, magnetized wind. The rotation measure we measure becomes a snapshot of the magnetic storm it had to navigate at that precise moment in its orbit. This single measurement transforms the burst from a mere flash into a probe of invisible forces. We cannot see magnetic fields across billions of light years, but we can measure how they sculpt the light that passes through them. The high rotation measure of this signal is a stark reminder that these cosmic explosions do not happen in a void. They are born within and must escape from landscapes of incredible magnetic fury, allowing us to sense the invisible architecture of power that shapes the distant cosmos. That magnetic fingerprint is a signature of natural fury, but the very first time such a regular pulse was heard, it sparked a very different fear. In the quiet of a Cambridge laboratory in 1967, a young doctoral student named Jocelyn Bell Burnell was reviewing miles of paper chart recordings from a new radio telescope she had helped build. The telescope was designed to study distant quasars, but Bell noticed something strange, a bit of what she called scruff on the chart. It was a faint, rhythmic pulse, a steady tick-tick-tick arriving every 1.337 seconds with a precision that rivaled the best atomic clocks on Earth. The signal was so unnervingly regular, so perfectly artificial in its timing, that the small team had to confront a staggering possibility. Had they truly stumbled upon a beacon? In the privacy of the control room, they half-jokingly labeled the source LGM-1 for Little Green Men. The name was a nervous joke masking a profound and serious consideration. For a few tense weeks, they secretly investigated the signal as a potential sign of extraterrestrial intelligence. They ruled out terrestrial interference, human-made satellites, and any known natural object. The pulse was too fast for a variable star, too slow for a white dwarf. Its clockwork regularity seemed to point to only one conclusion: a civilization was out there, broadcasting a steady signal to announce its presence. The weight of that possibility was immense. Bell later recalled the atmosphere as one of both terror and excitement, the terrifying thought that they might have to make a world-altering announcement. The mystery was resolved not by finding the aliens, but by finding more of the same signal. Bell soon discovered another pulsing source in a completely different part of the sky, then another. It was statistically impossible for multiple alien civilizations to be using the same precise frequency and pulse rate to communicate. The truth was even more extraordinary than little green men. They had discovered a previously unknown type of star, a cosmic lighthouse of unimaginable density. The source was a rapidly spinning neutron star, the collapsed core of a massive sun that had died in a supernova. As it spins, beams of radiation shoot from its magnetic poles, and if those beams sweep across Earth, we see a regular flash with each rotation, a pulsar. LGM-1 was the first, now known as CP1919. This moment is the foundational parable of modern radio astronomy. It is the story of how the most promising candidate for an artificial signal ever found turned out to be a revelation of natural cosmic engineering far beyond our previous imagination. The search for a whisper from another mind led directly to the discovery of a whole new class of stellar corps, proving that the universe is capable of creating clocks more precise than anything we can build. That initial leap to little green men was not a failure of science, but its essential first step, a testament to the courage required to follow the evidence, even when it points toward the unbelievable, only to find a reality that is, in its own way, even more incredible. The clockwork precision of a pulsar showed us nature's own engineering, but some signals emerge from places where such violence seems impossible. FRB 2019-0711 was traced to a galaxy that defies the typical profile. This was not a small, messy dwarf galaxy churning with newborn stars. It was a massive, mature spiral, a cosmic metropolis that had settled into a quiet middle age. In this galaxy, the frenetic era of star formation was largely over. Its spiral arms were not blazing stellar nurseries, but quieter neighborhoods of older, stable stars. This location is a profound puzzle. Our leading theory tells us fast radio bursts are the cries of young, violent objects, magnetars born from the explosive deaths of massive stars. Such stars live fast and die young, so we expect to find their remnants in places where stars are being born right now. A quiet galaxy should, in theory, be a quiet place for radio bursts. Its presence there forces us to reconsider the life cycle of these cosmic engines. If the burst did not come from a stellar toddler, perhaps it came from a senior citizen that found a second wind. The most compelling explanation involves a binary system resurrection. Imagine an old neutron star, the cold, slowly spinning remnant of a supernova that exploded billions of years ago. It has been drifting silently through the quiet galaxy for eons, but in the dense stellar environment of a galactic core or a globular cluster, it might have captured a companion, perhaps a white dwarf or a normal star. Over astronomical time, this companion could begin to transfer material onto the dormant neutron star. This infalling gas acts like a cosmic starter cord, spinning the neutron star up to incredible speeds and potentially rejuvenating its magnetic field. This process, called accretion, can effectively resurrect the dead star, turning it back into a powerful, magnetar-like object capable of producing colossal bursts. It is a stellar phoenix bursting back to life in a galaxy that had long forgotten such violence. This discovery dramatically expands the possible homes for these signals. It tells us that the universe can hide these explosive engines not just in its stellar nurseries, but in its retirement communities as well. A fast radio burst is not always a birth announcement. It can also be the sound of a sleeping giant, stirred awake after a billion-year slumber by the gravitational pull of a companion. While the hunt for brilliant flashes continues, some of the universe's most persistent whispers come from much closer to home. Just over 11 million light-years away, a small, tilted spiral galaxy named NGC 247, also called Cetus A, spins quietly in the constellation of the Sea Monster. For decades, radio telescopes have kept a patient watch on this galactic neighbor, and they have documented a curious phenomenon. From the galaxy's central region, a faint but unmistakable radio glow fluctuates over time. It is not a sudden burst or a repeating pulse, but a slow, rhythmic change in brightness, a long-term heartbeat of radio energy emanating from its core. This is not the deafening roar of a quasar or the brilliant flare of a magnetar. It is a low, steady hum that occasionally swells and fades, the signature of a cosmic engine idling in the dark. The most logical suspect for this activity sits at the very heart of NGC 247, a supermassive black hole, but this black hole is not a voracious monster. It is quiet, underfed, and relatively dormant. The variable radio emission suggests it is not entirely asleep. Occasionally, a wisp of gas, a stray star, or a cloud of dust might stray too close, spiraling into the gravitational well. As this material is torn apart and heated, it emits radiation before vanishing across the event horizon, causing the radio glow from the galactic center to brighten slightly. This fits the model of a low-luminosity active galactic nucleus, a faint cousin to the blazing quasars that light up the early universe. Yet, the specific mechanisms behind this particular galaxy's variable heartbeat remain puzzling. Why does the emission change on the timescales we observe? Is it due to instabilities in the thin accretion disk of material around the black hole, like bubbles rising in a slow boiling pot? Could it be linked to sporadic jet activity, where faint, narrow beams of particles are sporadically launched from the poles of the black hole, energizing the surrounding gas? Or does the answer lie in the environment itself, in the complex interplay between the black hole's influence and the dense star cluster that likely surrounds it? NGC 247 serves as a critical reminder. The catalogue of 40 unexplained signals is not filled solely with distant millisecond catastrophes. It also includes these slow-burning, nearby mysteries. While they may lack the dramatic punch of a fast radio burst, their persistent, variable nature offers a different kind of laboratory. We can observe them continuously, charting their slow changes over years and decades, building a detailed medical chart of a quiet galactic heart. This long-term monitoring reveals a universe thrumming with low-level activity, where even the most seemingly placid galaxies harbor central engines that flicker with secrets we are only beginning to decode. The slow, variable heartbeat of a nearby galaxy reminds us that cosmic engines come in many forms, but one signal arrived with an address so specific it felt like a cosmic postcard. FRB 2021-0206 was a brilliant one-time flash, but its legacy is defined by the precision of its home. Using the immense resolving power of the Very Large Array in New Mexico, astronomers did something extraordinary. They did not just trace this burst back to its host galaxy, a distant spiral. They pinpointed it to a single, dazzling neighborhood within that galaxy, a brilliant knot of light in one of its spiral arms. This was no random suburb. The location was a prolific stellar nursery, a region blazing with the ultraviolet light of countless newborn, massive stars. This precise localization is a powerful piece of evidence, a clue that feels almost too perfect. It strongly supports the leading theory that the engines of many fast radio bursts are the young, violent remnants of those very stars. In these stellar nurseries, the cycle of life and death operates on a frantic cosmic scale. Giant clouds of gas and dust collapse under their own gravity, igniting into stars many times more massive than our Sun. These stars are the rock stars of the cosmos, living fast and dying young. In only a few million years, a blink in galactic time, they exhaust their nuclear fuel. Their cores collapse, triggering a supernova explosion of unimaginable power that can outshine an entire galaxy. What remains is a city-sized cinder of unimaginable density, a neutron star. And if that neutron star is born with a magnetic field of almost incomprehensible strength, it becomes a magnetar. The environment of a star-forming region is the perfect cradle for such a monster. It is a place of constant violence where shock waves from previous supernova compress new gas clouds, triggering the next generation of stars and the next generation of potential magnetars. To find a fast radio burst originating from the heart of such a region is like finding a smoking gun at the scene of a specific type of crime. It tells us the burst is intimately linked to the most energetic stellar life cycle there is. The brilliant flash of radio waves could be the first cry of a newborn magnetar, a starquake on its turbulent surface, or a blast wave from its birth slamming into the surrounding nebula. This precise address does more than support a theory. It paints a vivid picture. We are not just detecting an anonymous explosion in the dark. We are witnessing an event deeply woven into the fabric of a galaxy's ongoing story of creation and destruction, a fleeting shout from a stellar maternity ward billions of light years away. Geminga's familiar pulse hides a far larger and stranger secret. This nearby stellar corpse spinning quietly in Gemini is encased within a colossal, invisible structure. Observations from gamma-ray telescopes have revealed a vast, diffuse halo of extremely high-energy radiation, a TV halo stretching for dozens of light years around the pulsar. This halo is a ghostly imprint of Geminga's past fury, a cloud of particles accelerated to nearly the speed of light by its powerful winds, now slowly diffusing into the surrounding interstellar space. But the mystery deepens when we switch our view to radio waves. Around this same region, astronomers have mapped large, faint, and complex structures of radio emission. These are not the clean, focused beams of the pulsar itself. They are sprawling, filamentary wisps and amorphous clouds that do not perfectly align with the gamma-ray halo or with any obvious features in the visible sky. The connection between the pulsar's current activity and these ancient radio whispers is unclear. One compelling possibility is that we are seeing the fossilized remnants of much older, more violent outbursts. Geminga, like all pulsars, was born in a supernova explosion and was likely far more energetic in its youth. The radio structures could be the fading echo of a gigantic pulsar wind nebula from that earlier era, a bubble of magnetized particles inflated by the young star's fierce winds, now distorted and swept into strange shapes by its motion through the galaxy. Another idea points to a more subtle interaction happening right now. Geminga's present-day wind, though weaker, is still streaming out into space. This wind is a torrent of charged particles carrying the pulsar's magnetic field. As this wind slams into the existing interstellar medium, a thin, uneven gas of hydrogen and other elements drifting between the stars, it can create shock waves and turbulence. These collisions can energize electrons, causing them to spiral along magnetic field lines and emit the faint, diffuse radio glow we detect. The complexity arises because the interstellar medium is not a smooth, uniform pool. It is a chaotic sea with currents, densities, and magnetic fields of its own. The interaction between Geminga's wind and this messy environment could produce the patchy, irregular radio features we see, a signature that is unique to this specific pulsar's journey through this specific patch of galactic real estate. Geminga teaches us a humbling lesson. Even an object we think we know, a pulsar we have catalogued and studied for decades, can be the center of an unresolved mystery. Its unexplained radio halo is a reminder that the cosmos is layered. Behind the clear, periodic tick of a cosmic clock, there often lies a much slower, more complex story written in faint static, a story of ancient violence and ongoing, invisible struggle between a dead star and the galaxy it travels through. The universe's radio whispers often arrive with a distinct tone, a signature that reveals their violent birth. Most fast radio bursts sound like a deep, booming note that quickly fades into higher pitches, as if someone turned down the volume on a cosmic radio dial as they spun the tuner upward. This is because the physical processes that create them, like synchrotron radiation from electrons spiraling in magnetic fields, naturally produce more power at lower frequencies. It is a familiar sound in the cosmos, but then there is FRB 2018-0301A. This burst broke the pattern. Its spectrum was flat. To understand why that is so strange, think of the sound of rain on a roof. Normally, the large, heavy raindrops make a deep, resonant thud, while the tiny droplets create a faint, high-pitched patter. The big drops are much louder. A flat spectrum is the opposite of that. It means the burst was just as bright, just as intense at its highest radio frequencies as it was at its lowest. Every note in its chord, from the deep bass to the piercing treble, screamed with equal power. This is not how most cosmic explosions behave. A flat radio spectrum points directly at a different kind of physics altogether, one involving coherent emission. Imagine a crowd of people in a stadium. If they all clap at random, different times, you hear a chaotic, general roar. That is like the incoherent emission from a typical synchrotron process. But if that entire crowd claps in perfect unison on the exact same beat, the sound becomes a single, powerful thunderclap. That is coherent emission, where countless particles or waves act in lockstep, amplifying each other to produce an intense, focused signal. For a burst to have a flat spectrum, it suggests its radio waves were born from such a coordinated, unified event within an extremely compact region. This immediately challenges the standard toolkits astronomers use to explain these flashes. The popular models of synchrotron radiation or curvature radiation, where particles whip along bent magnetic field lines, struggle to produce such a perfectly even signal across all frequencies. FRB 2018-0301 forces us to consider engines that can orchestrate this kind of unified blast. One possibility lies in the sudden, catastrophic release of magnetic energy in a tightly wound region on or above a magnetar's surface, a kind of magnetic short circuit that unleashes a coherent radio shockwave. Another might involve a dense, magnetized plasma near a black hole or neutron star undergoing a collective, wave-like instability that radiates with one clear voice across the entire radio band. This single, flat spectrum burst is a quiet rebel. It tells us that among the 40 unexplained signals, some may not be coming from the chaotic aftermath of an explosion, but from a momentary, perfectly tuned resonance within a cosmic instrument we have yet to fully understand. The universe is not only built of light but of shadow. Among the 40 unexplained signals, some of the most profound mysteries are not brilliant flashes, but vast, silent structures that glow only in the quietest part of the radio spectrum. This is the story of the Dark Galaxy Surveys, a search for the cosmic missing. Astronomers have long hunted for a theorized but never seen object, a dark galaxy. Imagine a massive cloud of hydrogen gas, enough to birth billions of stars, but where for some reason star formation never ignited. This would be a galaxy of pure potential, a ghostly island of primordial material drifting through the void. To find such an object, you cannot look for starlight. You must listen for a very specific whisper, the 21-centimeter line. This is the faint radio hum emitted by neutral hydrogen atoms when the spin of their single electron flips. It is a universal fingerprint for cold gas. For decades, radio telescopes have mapped the sky at this frequency, cataloging the distribution of hydrogen to trace the structure of the universe. And sometimes they find something that should not be there, an extended, diffuse cloud of 21-centimeter emission with no visible galaxy at its heart. These are the unexplained radio sources that could be our first glimpse of a dark galaxy. One famous candidate is Virgo 21, a cloud of hydrogen discovered in the Virgo cluster with no optical counterpart. Its mass, deduced from the width of its 21-centimeter line, suggested it held enough dark matter to be a substantial galaxy, yet it was completely invisible in telescopes that capture starlight. The excitement was palpable, a potential first discovery of a galaxy made almost entirely of dark matter and gas, but the cosmos is rarely so simple. Further analysis suggested a more chaotic, though no less fascinating, origin. Virgo-He 21 may not be a pristine dark galaxy at all. It could be tidal debris, a long, stretched-out ribbon of gas ripped from a visible galaxy during a close encounter with another, left hanging in intergalactic space like cosmic spittle. This is the core challenge of the search. When you find a cloud of radio-emitting hydrogen with no stars, is it a failed galaxy or just the wreckage of a successful one? The answer lies in the dynamics, the internal motion of the gas. In a true dark galaxy, the hydrogen should rotate in a coherent, disk-like pattern, held together by its own gravity and a halo of dark matter. In tidal debris, the motion is chaotic, a stream of material being pulled apart, not holding itself together. Distinguishing between the two requires exquisitely sensitive observations, and often the data remains ambiguous. These unexplained radio sources represent a different class of mystery entirely. They are not milliseconds long, but millions of light years across. They are not about catastrophic energy release, but about profound absence, about why some clouds of gas remain forever dark while others blaze with stellar life. Finding a true dark galaxy would revolutionize our understanding of galaxy formation, revealing that the recipe for building a star city can sometimes fail, leaving behind only a silent radio whisper of what might have been. Until we can peer into the dynamics of these ghostly clouds with absolute clarity, they remain some of the most haunting and persistent shadows in our radio maps of the cosmos. That search for the universe's missing dark matter is a hunt for vast, silent structures, but sometimes the most crucial evidence arrives in a flash of light from a completely different part of the spectrum. The universe speaks in many languages, not just radio waves. It shouts in X-rays, glows in infrared, and screams in gamma rays, the highest energy form of light. To truly understand a fast radio burst, we need to hear it in more than one voice. This is the promise of multi-messenger astronomy, and it brings us to FRB 220509A. This particular burst was a brilliant, one-time event detected by the CHIME telescope in May 2022. What made it extraordinary was a faint, tentative whisper from a different kind of listener. Around the same time this radio burst lit up, a space-based gamma-ray observatory reported a possible, unconfirmed flare from the same general patch of sky. The timing was suspiciously close. It was not a guaranteed match. The data was too fuzzy for a firm declaration, but the coincidence sent a jolt of electricity through the astrophysics community. Why would a simultaneous gamma-ray flash be so revolutionary? Because it would act as a cosmic interpreter, directly translating the radio burst's mystery into a language of known physics. Gamma rays are the signature of the most violent events in the cosmos. They are produced in the furnaces of supernova explosions, in the relativistic jets of black holes, and in the final, catastrophic mergers of neutron stars. If a fast radio burst arrives hand in hand with a gamma-ray flare, it tells us beyond any doubt that the radio scream is a side effect of one of these titanic cataclysms. For instance, imagine two neutron stars, each more massive than our Sun but crushed into a city-sized sphere, locked in a final, decaying orbit. As they spiral together and collide, they would unleash a firestorm of gamma rays in a short, intense burst known as a short gamma-ray burst. The merger would also create a turbulent, magnetized environment that could, in theory, produce the coherent radio flash we see as an FRB. A confirmed detection would be the smoking gun, directly linking these two phenomenal events. Or consider a supernova, the death of a massive star. The collapsing core could birth a rapidly spinning, highly magnetic neutron star, a magnetar. The birth pangs of that magnetar, colossal quakes on its surface as it settles into its new form, could blast out both a high-energy gamma-ray flare and a focused beam of radio waves. A simultaneous detection would lock that theoretical picture into observed reality. The tantalizing, unconfirmed link with FRB 220509 highlights both the immense potential and the staggering difficulty of this hunt. The universe is not a controlled laboratory. These events are rare, unpredictable, and over in milliseconds. Coordinating observations across the globe and in space with telescopes that must be pointed at the right place at the exact right millisecond is a monumental challenge. A gamma-ray satellite might be looking at the wrong part of the sky. A radio telescope might be offline for maintenance. The faint gamma-ray whisper might be lost in the background noise of the cosmos. Yet the pursuit continues because a single, confirmed multi-messenger event would do more than solve one mystery. It would throw open a door, allowing us to use these brilliant radio flashes as universal markers, beacons that point our most powerful instruments toward the instant of cosmic catastrophe, so we can witness the full, multispectral fury of the universe's most extreme physics. The line between a cosmic signal and a terrestrial mystery can blur in the human imagination. In September 1994, over 60 children at the Ariel School in Ruwa, Zimbabwe, reported a shared, startling experience. During their morning break, they said a strange craft landed in a field beyond the schoolyard, and unusual beings emerged. The event, intensely investigated and debated for decades, remains one of the most compelling mass witness UFO encounters on record. Years after the initial incident, a different layer was added to its lore by some independent investigators. They returned to the now overgrown field and, using handheld radio frequency meters, claimed to detect persistent, anomalous readings. The reports suggested odd spikes in certain frequency bands, a residual energy signature that defied easy explanation. These claims exist entirely outside formal science. No peer-reviewed paper has ever been published on these measurements. The equipment used was basic, the methodology was not controlled, and the findings have never been replicated by an academic institution. In the strict catalogue of the 40 unexplained radio signals from beyond our galaxy, this terrestrial event has no place, yet its story is irresistibly drawn into the same cultural orbit. It represents a powerful human impulse to take something profoundly unexplained and search for a technological fingerprint, to translate a visual mystery into a quantifiable signal on a dial. The Ariel School claims connect to our broader theme not as evidence but as a mirror. They show how the deep desire to find patterns, to validate the extraordinary with an instrument's reading, extends from the vastness of space to a small field in Africa. When we point our telescopes at the stars, we are driven by the same fundamental curiosity that sent those investigators into the brush with their meters. We are all listening for a signal, any signal, that tells us we are not alone in a universe of mysteries, whether those mysteries hover at the edge of a galaxy or at the edge of a schoolyard. The silence after a single brilliant flash can be the most profound mystery of all. In July 2023, the CHIME telescope added another stark, lonely point to its growing map of cosmic transients. This was FRB 2307-18A, a powerful, millisecond burst of radio energy that announced itself just once and then vanished forever into the background hum of the universe. Its detection triggered a well-rehearsed sequence in the world of astronomy, a cosmic triage for these fleeting events. The first step is always the dispersion measure. By analyzing how the burst's different radio frequencies were stretched and delayed, astronomers could immediately tell it had traveled a very long way, through billions of light years of intergalactic plasma, placing its origin far outside our Milky Way. The next step is localization. CHIME array of antennas provided a rough sky coordinate, a patch of the heavens to point other, more precise instruments toward. The call went out across the global network of telescopes. Optical observatories swung toward that patch, taking deep images to search for a faint, distant galaxy that might be the burst's home. Even more critically, radio telescopes like the Very Large Array listened intently at the exact coordinates. their sensitive ears tuned for the slightest hint of a follow-up whisper, a second burst that would transform this one-off event into a repeater, a persistent source we could study. For FRB 2307-18A, the follow-up revealed nothing. No host galaxy was immediately obvious in the optical images. No repeating signal ever came. It was a solitary shout in the dark, a brilliant flash with no afterglow and no address. This is the overwhelming norm. For every repeater like FRB 121102 with its predictable cadence, there are hundreds, perhaps thousands of these one-time events. They dominate the statistics. Each one is a cosmic dead end, a closed case with no further evidence. The leading theory for their origin is as final as it is violent. These single bursts may be the death knells of objects that cannot survive their own fury. Imagine a magnetar undergoing a cataclysmic starquake so immense it cracks the star's entire crust, releasing a blast of energy that vaporizes the magnetic field structure that powered it. The star might literally tear itself apart in the process, or consider the merger of two neutron stars, a collision of ultimate densities. In the final milliseconds before they smash together and collapse into a black hole, their wildly interacting magnetic fields could twist into a configuration that unleashes one, and only one, colossal beam of radio energy directly at Earth. A moment later, the objects that created it cease to exist, swallowed by the singularity they birth. These non-repeaters are the universe's most dramatic suicides. They leave no engine behind to power a second act, no lighthouse to flash again. They are the ultimate transient, a testament to the fact that some of the cosmos's most brilliant signals are also its most self-destructive, leaving behind only a fading ripple in our data and a permanent question mark in the sky. The final signal on our list is not a fleeting whisper, but the oldest shout in the universe, permanently etched across the entire sky. It is the cosmic microwave background, the faint afterglow of the Big Bang itself. This is the universe's baby picture, a snapshot of the cosmos when it was just 380,000 years old, a sea of hot plasma that cooled into a bath of microwave radiation as space expanded. For decades, this signal has been the bedrock of modern cosmology, a near-perfect map confirming our basic story of the universe's birth and expansion. Yet when scientists look at this map with exquisite precision, something unsettling emerges. The cosmic microwave background is not perfectly smooth. It contains subtle wrinkles, hot and cold spots where matter was slightly denser or thinner. These wrinkles should be randomly distributed like the static on an old television screen. But they are not. On the largest scales, these temperature fluctuations show strange, coherent alignments. One of the most famous is dubbed the axis of evil. This is not a literal axis of destruction, but a statistical oddity where the hot and cold spots seem to line up in a particular direction across the sky. An alignment that defies the core principle of cosmology, that the universe should look roughly the same in every direction. It is as if the entire cosmos has a faint, preferred orientation, a cosmic fingerprint pointing in one specific way. Another anomaly is the cold spot, a region of space far colder than our models can easily explain, a vast, quiet void in the ancient light. So what could these large-scale quirks mean? One possibility is that they are simply a statistical fluke, a cosmic illusion created by the fact that we only have one universe to observe. Perhaps if we could see 1,000,000 different universes, one of them would have an anomaly this strange, and we just happen to live in that one. But if they are real features, the implications are staggering. They could be a bruise from before the Big Bang, an imprint from an earlier phase of the cosmos, or evidence that our universe is not infinite and isotropic, but has a larger scale structure we are only seeing the edge of. They might even suggest our solar system has a peculiar motion relative to this primordial frame, placing us in an unusual location in the grand scheme. These anomalies in the cosmic microwave background are the ultimate radio signal, a message from the first moment of time that we have received but have not yet fully decoded. They remind us that our most fundamental map of reality may still contain uncharted territories, written in the faint, cold light of creation itself. Taken together, these 40 whispers form a new kind of cosmic language. Each signal, whether a solitary scream from a dying star or a repeating heartbeat from a galactic nursery, is a single word in a sentence we are just learning to read. The sheer diversity of these sources is the first great revelation. We have confirmed the culprit in our own backyard, a magnetar in the Milky Way flashing in radio and X-rays. Yet we also listen to enigmas billions of light years away that repeat on a perfect 16-day schedule, or blaze with a flat spectrum that defies our emission models. This is not a single mystery with one answer. It is a sprawling zoo of cosmic radio transients, each revealing a different facet of extreme physics. The journey itself is profound. We have moved from a state of isolated confusion, where a single burst like the Lorimer discovery was met with deep skepticism, to a new reality. Fast radio bursts are now a recognized astrophysical population, as established as pulsars or supernova. They are no longer anomalies, but expected, if unpredictable, features of a violent universe. This shift changes everything. It means we are no longer just hunting for oddities. We are now taking a census, classifying families, and building a statistical understanding of how often these events occur and where they like to live. But the true power of these signals lies not just in what they are, but in what they allow us to see. Every burst, explained or not, is a tool. As each flash travels across the cosmos, it does not move through empty space. It slices through the thin, magnetized plasma that floats between the stars and galaxies, the very fabric of the cosmic web. The signal carries the scars of that journey. By measuring how its frequencies are smeared, twisted, and scattered, we can reverse engineer the conditions along its path. We can map the distribution of invisible matter, gauge the strength of magnetic fields in the voids, and even test our models of the universe's expansion. A single millisecond burst becomes a probe, illuminating the dark highways of the cosmos. These whispers are more than just cosmic fireworks. They are flashlights in the dark, turned on for an instant, allowing us to see the hidden architecture of everything. These 40 cosmic whispers, from the solitary wow to the rhythmic repeater, tell a story of human curiosity meeting cosmic chaos. Most will not be messages from other minds, but something equally valuable, natural phenomena pushing the very limits of physics. The journey from dismissing a single blip as a microwave oven to recognizing an entire class of celestial catastrophe is how science truly advances. Each unexplained signal is not a failure of understanding, but an invitation to look deeper, to build a better telescope, to write a more elegant equation. This process of questioning, testing, and revising is the engine of discovery itself, and that engine is about to roar to life. We stand at the threshold of a new era of listening. Projects like the Square Kilometre Array, a continent-spanning network of radio dishes, will soon come online. With sensitivity thousands of times greater than today's instruments, it will not just hunt for these whispers, it will hear a chorus. Instead of 40 unexplained signals, we may soon catalog millions, transforming rare anomalies into a rich data set that maps the violent heartbeat of the universe across cosmic time. We will pinpoint their homes with surgical precision, catch them in the act with other forms of light, and finally decode the physics of their birth. The static is about to resolve into a symphony, so keep looking up and stay curious. The universe has been whispering for billions of years. We are only just beginning to learn how to listen.